Okay, let's talk about a problem that I know drives a lot of data engineers crazy. You've got a Spark job, you hit run, and you just wait and wait, and what should be a simple join turns into an absolute performance nightmare. And look, this isn't just some made-up number. This is a real-world, pull-your-hair-out kind of problem. You have this massive billion-row transaction table, and you just want to join it against a tiny little lookup table with, say, product categories. It seems so simple, but suddenly your pipeline grinds to a halt. We're talking jobs that are 10, maybe even 50 times slower than they should be. So what's really going on under the hood? To solve this mystery, we first need to understand the two main suspects, the two primary ways Spark joins data. Once we get that, we'll know exactly how to fix it. When Spark needs to join two tables, it has a big decision to make. Does it go with the slow, steady, and super reliable sort-merge join? Or does it go for the speed demon, the lightning-fast broadcast join? The choice it makes is absolutely critical for your job's performance. The real story here is in that data movement row. The sort-merge join creates this massive traffic jam on your network called a shuffle, where all the data from both tables gets moved around and sorted. It's expensive and slow. But the broadcast join, it completely avoids that shuffle for the big table by taking the small table and just sending a copy of it to every single machine. And here's why that's so incredibly efficient. The driver node grabs that small table, zips it across the network just once to every worker, and then that's it. From that point on, the join happens entirely locally on each machine. No more network chatter for the big table. It's a huge win. Okay, so if the broadcast join is so clearly faster in these situations, why on earth doesn't Spark just use it every single time we have a small table? Well, this is where we get into how Spark actually thinks. Spark has this incredibly smart brain called the Catalyst Optimizer. Think of it like a GPS for your data query. It looks at your code, it looks at the stats of your tables, and it tries to calculate the fastest, most efficient route. But like any GPS, it's only as good as its map data, and it relies on one very specific number to make this call. And this is it. This is the magic number, 10 megabytes. By default, Spark's configuration, spark.sql.autoBroadcastJoinThreshold, is set to just 10 MB. This means Spark will only even consider broadcasting a table if its own estimate says that table is smaller than this tiny threshold. And that's the million-dollar question, isn't it? This is the Achilles heel of the whole system. The optimizer is smart, but it's not psychic, and sometimes its size estimates are just wildly, completely wrong. These are the optimizer's blind spots. For example, maybe you filtered a huge table down to just a few thousand rows, but if the table statistics haven't been updated, Spark still sees the original giant size. That's what we call stale stats. And because of that bad information, it makes a super conservative and slow choice: the sort-merge join. But here's the good news. You don't have to just accept the optimizer's bad decision. When you, the developer, know better, when you know that table is small enough to be broadcasted, you can actually step in and take control. The most direct way to do this is with something called a join hint. It's basically you telling Spark, hey, I don't care what your estimate says. I know better. Broadcast this table. As you can see, you can wrap your data frame in a broadcast function in PySpark or use a special comment in SQL. It's a direct order to the optimizer. Now, if you find yourself using hints all the time, you might want a more permanent fix. On clusters with plenty of memory, you can simply increase that autoBroadcastJoinThreshold config. Bumping it up to 100 or 200 megabytes tells Spark it has permission to be more aggressive and automatically broadcast larger tables, saving you a ton of hassle. All right, now that we've seen the problem and the solutions, let's wrap this all up into a simple, practical toolkit you can start using right away. So, here's your playbook. First, diagnose the problem. Use the .explain method on your data frame to see the physical plan. If you see a sort-merge join with a small table, you've found your culprit. Second, intervene with a broadcast hint to get that immediate speed boost. Third, for a long-term fix, configure the threshold. And finally, maintain your table stats to help the optimizer make better decisions on its own. By understanding these mechanics, you can finally take control. You're no longer just a victim of a slow query. You are now the engineer who can look at the plan, understand why Spark made the wrong choice, and deliberately guide it to the fastest possible result. You're in the driver's seat.